Hello. Hello. Hi, everybody. All righty. For those of you who don't know me, I'm John Mulcahy. I'm the director of the Carnegie Observatories and the deputy for science for Carnegie Science. I'm really excited. Tonight you get to hear a topic. I realize we started these lectures 22 seasons ago, as you can see, and this is a topic we have never had in the 22 seasons, which is remarkable. Radio astronomy is super important for astronomy, just we haven't had anybody to talk to you about it. So this will be a very exciting lecture, so I'm sure you will enjoy it. I should say that we are all on a high at Carnegie because of the big eclipse last week. That was why I wasn't here on April 1st. I was already in Dallas. We had 30 astronomers in Dallas last week. People were there for the full week. We went to over 40 schools. We saw over 15,000 children. We gave out glasses to, thank you. We gave out special solar glasses to 1 million people in the Dallas area. So it was really a remarkable thing. And it's been a week and I'm still exhausted. It was amazing and exhausting. And the clouds cleared just in time for us to see the eclipse in Dallas. And I know many of you told me as you were coming in you had the chance to see it. So if you haven't, 2026, Spain, Greenland, or Iceland, we're already figuring out where we're going to be. But there you go. If you've never seen a total solar eclipse, I said this 1,000 times last week, you must experience it once in your lifetime. I know you think you've seen an eclipse, but until you've seen a total solar eclipse, you haven't seen an eclipse. Anyhow, Erica already thanked all of the folks here at the Huntington, our own volunteers. I also want to thank the Norris Foundation, which provides funding for this lecture series. And that's super important for us, and we're so excited to be able to continue the series and have it be such a popular event. So let me get going with tonight's speaker. Allison Matthews did her PhD at the University of Virginia, working on radio astronomy. She worked with one of the real pioneers of the field, Jim Condon, and she came to Carnegie in 21 as a Carnegie Vera Rubin Fellow. The name Vera Rubin should be familiar to many of you. She was a very famous Carnegie astronomer who discovered dark matter and galaxies. So we created a fellowship in Vera's honor recently, and so Allison is our current one. And I think you're just going to be super excited to hear all the amazing things she's doing in radio astronomy. So with that, let's go ahead and bring Allison out. Allison, come on out.
Thank you so much, John. It's been a pleasure being at Carnegie, and I have the privilege of, until last fall, being the only radio astronomer at Carnegie, so I think I am the only one qualified to talk about this topic, which makes my job pretty easy. All right, so we're gonna go on this journey together, talking about the history of radio astronomy and how much it has provided our knowledge of the universe. So one of the biggest questions we have as astronomers is, where did we come from? What are our origins? How did something like our Milky Way form when our universe just began as a soup of random particles? And so it's natural that we might look at our own galaxy first in order to answer this question. And so this is a picture of the center of our Milky Way from Las Campanas Observatory, which, as you probably know, is where Carnegie has its world-class telescopes in Chile. And you can see this beautiful array of stars of varying colors. And you can also see a lot of dust. And dust is a big problem in astronomy. Well, for optical astronomers. So dust prevents us from seeing so much of our own galaxy, and it turns out the problem doesn't get any better as you go further back in time, back to the eras where most of the stars in our universe were formed. So we can try to do better, and we can look at longer wavelengths, and longer wavelengths allow us to see through more of the dust, because dust scatters light that is about the same, that's wavelength is about the same as the dust grain size. And so we can go to an infrared wavelength. So this is an image from the Spitzer Space Telescope. And you can see it looks a little different, but you still have this problem of all of this dust. And so I'm going to slowly transition to what we see in the radio and hope that you can appreciate all of its wonder. So this is what the center of our galaxy looks like at radio wavelengths. And you're probably familiar with this image since it was posted as the advertisement for this talk. And it encapsulates so much of what we do know and what we don't know about physics and galaxies and the engines that are driving all of this emission. There are structures in here that we still don't understand. These strange filamentary structures are things that we have guesses for, but not really conclusive ideas and theories to produce. And so there really aren't many words I can say to capture how wonderful this image is, but it indicates that going to radio wavelengths provides us this entirely new window into our universe. So that's our Milky Way, but we know that our universe has gone through many different eras, starting from inflation, this rapid acceleration in the space-time, all the way through today. What I'll be talking about mostly is just from the period of time where we can see stars. And stars are the building blocks of galaxies. They are what all of the elements in our world came from. And we can measure how much stars are forming as a function of time. And this gives us information about when most of the structure in our universe formed, when most of the mass formed, or the stellar mass. And it's this really crucial curve that looks quite simple, but it encodes so much about our understanding of the universe. And of course, to make such measurements, we have to get by the problem of dust. Dust is literally everywhere, and it's not the dust that might be, under your seats or under your couch. It's actually very similar to the dust that's in the air of Los Angeles, the smog that prevents us maybe from seeing the mountains so clearly. And just to emphasize how bad of a problem this is, the same curve is shown on the left, but then on the right, I have the same measurements, but shown at two different wavelengths. So this top wavelength, this is in the infrared, and again, infrared is longer wavelength, so it's less affected by dust. And the bottom wavelength is star formation rate measurements taken in the ultraviolet light. So this is really short wavelength light, which is primarily emitted by massive stars. And you can see, it's quite a big difference. And we've learned a lot about dust over the years, and we can make corrections for these measurements, but dust is not the same everywhere. And so these corrections are highly uncertain. And to make matters worse, if we look at the amount of dust in the universe, we see that the amount of dust peaks just when the star formation peaks. So if our goal is to understand when most of the galaxies formed or when they formed most of their stellar mass, those measurements are the most uncertain at the period of time when they are doing the most work. And so you might wonder, well, is this a problem for all galaxies or just, a handful? It's really all galaxies. So even our galaxy like the Milky Way, if you put it at this period of time in the peak of star formation, we would be missing, over 90% of the starlight that is normally used to measure how quickly stars are forming. So if only we had a way to measure star formation rates without worrying about dust. And this is where the journey of radio astronomy, for me, really begins. But to put it in context, I'm going to go back to the very, very beginning and talk about radio astronomy as this happy little accident that no one went looking for radio waves in the universe. They just happened upon them. And this is a theme that will keep coming back and back over this talk, that, if you just look around you, you might find something pretty cool. All right, so we'll leave Bob Ross alone for now. And our story begins in 1927 with the advent of transatlantic radio phones. And so on January 7th, 1927, the first transatlantic telephone call was made using radio wavelengths. And ultimately, this was a big success. The president of Bell Labs, or the Bell Telephone Company, was able to talk to the mayor of London, and many more phone calls were made, but ultimately they noticed that there was this major problem, which is static. And static made it very difficult to, understand each other, as you might imagine. And to improve upon this, Bell Labs decided to hire a young engineer out of the University of Wisconsin named Karl Jansky. He doesn't look very excited, but he was about to do something very exciting. And so his task was essentially to figure out what was the source of all of this static, and then ultimately, that is a necessary information in order to do something about it. So what's crucial about Jansky's task is he had to determine the direction of this static interference. And so he had to go about building a radio telescope. And so in 1932, when Jansky was doing this, no one had really built a radio telescope before, or at least one that could see in specific directions of the sky. And so he kept things pretty simple. He needed a base to put his telescope on, and he made this round because if you have to measure the direction of arrival of a signal, you want to be able to point your telescope at different parts in the sky. He needs something to actually rotate his telescope on, so he literally took a Model T Ford, took the tires off, and that became essentially his merry-go-round telescope. He constructed this, structure just out of wood beams, painted them white, and then most importantly, this is the thing that actually makes it a radio telescope, he added a bunch of wires. So this telescope probably doesn't look like one you might imagine, but it ended up founding the entire field. And so we have a copy of Jansky's telescope, a reproduction, actually in Green Bank, West Virginia, where the Green Bank telescope is. And so this is to commemorate Jansky's telescope, but it's no longer in operation. We can do a lot better now. But this is what it looked like at the time. This is Jansky. He still doesn't look very excited. And so what he did is he took this contraption and he rotated it around this base and measured how much power or radio signal he was getting at different directions in the sky. And so this is a plot that he published, and I had a hard time understanding what was going on here, so I'm going to try to walk through it. But basically, you can see on the top that these are the different directions, north-south, or northwest-southeast. And he saw that there is this persistent signal, this peak, that indicated that there was some source there. But the source was moving in direction across the sky. At first, he thought that this was the sun. It happened to be pretty much aligned with the sun, and at that time, physicists had guessed that the sun could produce radio emission. But he waited. He was very smart. He waited before announcing a discovery. And 6 months later, the signal was still here, but no longer aligned with the sun. And then he noticed something else very important. The signal returned to the same point in the sky in 23 hours and 56 minutes, which is very close to 24 hours or a day. But what's very important about these 4 minutes is it is what we would call a sidereal day. So since the Earth is orbiting the sun, it only takes 23 hours and 56 minutes in order to look at the same exact point in the sky. You gain those 4 minutes, basically. And so he knew from this that this signal must be coming from outside of our solar system, which is how he determined it was of interstellar origin. And he read some astronomy books, he talked to some people, and put together that this signal was coming from a region of sky very near the center of our galaxy. So he published these results both within Bell Labs and also in astrophysical journals. And this made big news. This made the front page of the New York Times that we had detected these radio signals from the center of our Milky Way. Unfortunately, most astronomers at the time couldn't have cared less about Jansky's discovery. And so ultimately, although Jansky wanted to build another telescope and pursue this science further, Bell Labs considered his objective complete, and he was reassigned, and unfortunately and sadly never worked on radio astronomy again. So this is a picture of Jansky looking at this cartoon. This is probably staged. We know now that this is probably staged. But he's pointing near the constellation Cassiopeia, which we know is near the center of our galaxy. And so, to summarize, Jansky stumbled upon this hiss coming from the center of our Milky Way, but nothing in space had been seen in radio light before. This was our first indication that our universe emitted at radio wavelengths. In addition, partially the reason why astronomers didn't pay this much mind was because the emission was so powerful they couldn't really explain it with our current physics of the universe. And so they pretty much disregarded Jansky's discovery, except for one person. Okay, maybe not one person, but one person that did something about it. So we leave Jansky, who did his experiment in a potato field in New Jersey, and go to Illinois, the home of Reber. Reber is an extremely interesting person. I could have spent my entire talk talking about this one man, but I'll try to keep this somewhat brief. He was an avid ham radio operator. And so this is an example of what a ham radio license looked like at the time. This was his setup in his mother's home. And so from the age of like 15, he was contacting radio operators all around the world. He was extremely skilled. He built an antenna on top of his mother's house and was getting kind of bored. But he read about Jansky's discovery, and he knew that this was something super important. And so this is, some of Jansky's Reber's accolades. All these indicate all the different call signs that he was able to communicate with. He achieved something that they called working across all continents, which was a big feat at the time. He even helped with an Arctic expedition. He relayed some key messages from an Arctic expedition. And so you can imagine he was getting kind of bored. And he even said that there did not appear to be any more worlds to conquer in the radio. And so he read about Jansky's discovery, and he went to university professors and asked what they were doing about it. And unfortunately, the answer was mostly nothing. And so he has this great quote, "So I consulted with myself and decided to build a dish." So these are various pictures of, this is Reber feeding the receiver or fixing something on the telescope. This is where the measurements were actually being recorded. And so he built this 31-foot diameter dish in the vacant lot next to his mom's home in Illinois. He has been interviewed and said that the neighbors were really confused about what was going on, and they even thought that he was trying to control the weather, partially because when he stored the telescope, when it wasn't in use, he stored it, pointing straight up. And so Illinois, it's, pretty rainy there, and so all that rain would funnel right through that hole in the center of the dish, and was apparently something very scary, and his neighbors were probably not too much of a fan. But he built this dish with the goal of mapping out the emission that Jansky had discovered. So Jansky's telescope was able to see different directions, but it really couldn't do much more than that. Reber wanted to determine the exact points in the sky that this emission was coming from. And so this dish is considered the first real astronomical radio telescope. So, on top of building a dish, which took an entire year's salary of his money, he had to determine, well, what frequency or wavelength am I going to observe at? At this point in time, mostly everything in the universe that we knew about was a star or composed of stars. And we know that stars are primarily black bodies, so they emit radiation as like an opaque thermal object. And so Jansky's frequency that he found the center of the Milky Way at was way down in this tail of emission. So Reber thought, well, there's clearly the smart direction to go, which is where there should be stronger emission. And so after he finished constructing his telescope in 1937, he put on a receiver that was observing at 3.3 gigahertz. This is much, much higher frequency than Jansky's discovery. And surely this should have been more powerful at this frequency, but unfortunately Reber found nothing. And so he tried again, and he thought, well, maybe I went too far, I went over the peak, and I'm now seeing, the other side where it's very, very faint. And so he tried a little bit lower, and again, he found nothing. And so this became very puzzling. This didn't follow any of the physics that we knew about. And so finally, he tried again, much closer to Jansky's frequency, and finally detected galactic radio emission. So this was indicating that whatever was producing this radio emission was unlike any object or physics that we had previously known about. And so he wanted to publish these results in the Astrophysical Journal, but as you can imagine, submitting a paper when your institution is your mom's house in Illinois doesn't get taken very seriously. And so thankfully, he had been taking astronomy classes at the University of Chicago, and he convinced some of them to come see his facility, as well as some editors from the Astrophysical Journal. And eventually, they deemed his results credible, and he did get to publish his results. And so Reber was the first one to really map out the center of our galaxy. His maps didn't look anything like what I showed at the beginning or what was on the advertisements for this talk, but they were very significant. And more importantly, they indicated that something about the radio emission coming from, the center of our galaxy is unlike anything that we could explain with current physics. And it took over a decade longer for the correct theory to explain this was actually published. So 1940s, another big thing in the world was happening, World War II. And this introduced the rise of radar. So radar became extremely important in detecting enemy planes and warships. And it also included radar jamming, which was the flooding of the radio bands so that someone could not detect a plane or a ship coming. And it was said that in the UK, there was a post of this radar post trying, looking for German airplanes. And one day in 1942, they had this very terrifying realization that their signals were just being swamped by such intense radio emission that they had no chance of detecting any of their radar signals. And this was really concerning. But someone on the staff was a physicist in a previous, before the war, and he was aware that they had predicted that the sun should be able to emit at radio frequencies. And so he called some of his astronomy friends and asked if the sun was doing anything peculiar at that moment. And what was really quite fascinating was even though this was a period of time where the sun was at its minimum in its magnetic cycle, there was a massive sunspot. And so this sunspot was totally swamping all of their abilities to operate their radar, and was the motivation for many of the radio engineers who were operating these dishes to pursue after the war was over. And so after the war was over, many of the first objects that people studied were the things that were causing interference in the war. And so these were things like meteors, the moon, and the sun. These images were not taken then. These are very recent. But they show the power, again, of what you can see in the radio. So it looks like an optical image of the moon's surface, but it's actually a radar image. So the Arecibo telescope, rest in peace, would shoot radar beams out at the sun, or at the moon, sorry. And the Green Bank telescope in West Virginia would receive these beams. And they would pulse these so that they would cover the moon's surface, and they can detect craters, like this is Tycho's crater. And what's even more fascinating is that this isn't the surface, this isn't the dusty surface of the moon. This is actually about 10 meters below the dust of the moon. And so radio allows you to probe different depths and surfaces because of its such long wavelength. And then on the right, this is an image of the sun at radio frequencies. And it might not look very remarkable, but what you're actually seeing is not the surface of the sun, but the sun's atmosphere. You're seeing the chromosphere of the sun. And so right here, you see this red hot spot in the atmosphere. This corresponds to a sunspot below it. And so we can learn a lot about the atmosphere of the sun and try to understand why the corona of the sun is 1,000,000 degrees when the surface is only a few thousand, just by looking at the radio. So after studying the moon, sun, meteors, they expanded their horizons and started making maps of different sources. And some of these sources that they found were really sharp point sources, and they could be identified with what looked like pretty unremarkable but bright optical sources. And because of this, they became known as quasi-stellar radio sources, which was eventually shortened to quasars. And so this is a map from the teams at the University of Cambridge in the UK, which did many of these initial surveys, with the positions of all the extragalactic sources that they were seeing. But they didn't quite know what these sources were. They looked like stars, but they had this intense radio emission, and by this point, they realized that the sun is actually not a very bright radio source. We really only see it because it's so nearby. And so this couldn't really be credited to stars, and so they started trying to figure this out. And a big effort in this happened just down the street at Caltech. So they had a group operating this interferometer, which is just a series of radio dishes acting together as one. And they were compiling a catalog of the very pinprick bright sources. And they had colleagues who were using the Palomar Observatory, this 200-inch telescope, which was the largest at the time, to take spectra of these objects and try to figure out what they were. And they had been doing this for many years, and they saw objects with emission lines, but they couldn't identify which ones they were, until one of the astronomers there, Martin Schmidt, realized that those emission lines were actually very familiar. They corresponded to the Balmer series of the hydrogen atom. But they weren't lying at the wavelengths that they normally do. They were shifted to longer wavelengths. And what this allowed him to do was fit the distance to the quasars. And the first one he found was about 3 billion years away, or light years away, but he quickly found some that were 10 billion light years away. And this presented a big problem for understanding of the universe, because at that time, nothing had been seen that bright or that far away. So one of his colleagues supposedly went home to his wife and said something terrible happened at the office. And the terrible thing was that if these quasars were at the calculated redshift, or that's just astronomer lingo for distance, they would be 40 times brighter than the brightest known galaxies. And we had no way to explain this at the time. And it took a few years, but eventually, Lyndon Bell realized that you could power such intense emission through black holes. So black holes, we now know, occupy the centers of most galaxies. And as the material, the gas and the dust is accumulating around the black hole into an accretion disk, it heats up and starts emitting very strongly in radio frequencies. And sometimes these end up shooting giant jets into intergalactic space. They're really quite remarkable. And so this was kind of the first indication that all these quasars, which they found in the centers of galaxies, were actually black holes eating up so much of the material that it was producing these jets and emitting so much in the radio. So, to summarize that part, they didn't go looking for things, but they did find that these radio observations of quasars indicated that supermassive black holes are intense emitters due to their accretion disks, and nearly every galaxy has a supermassive black hole in its center. So quasars are interesting in their own rights for understanding the evolution of galaxies, but they had cosmological implications as well. So during this time, there were two competing theories for the evolution of the universe. One was steady state theory, which was essentially just that as time goes by, the universe is homogeneous and isotropic everywhere, and matter is created and stars are created as the universe expands. And this took into account Hubble's observation that galaxies are in fact traveling further and further away from each other, and space is itself expanding. Now, how quasars play into this is that we only see them really, really far away. And what this means is that the universe very far away is not the same universe that we live in locally, which was indication that the Big Bang Theory was providing a better explanation for these results. But thankfully, we had other radio astronomers working on this. Penzias and Wilson, who were, again, working for Bell Labs, they were actually working in the same old potato field that Jansky discovered the emission from, were using this really weird-looking horn antenna. And what they were doing was they were trying to determine the spaces between galaxies by their radio signals. Because, as I was saying before, if you can determine the spaces between those galaxies, you should be able to tell if space is expanding or not, depending on the distance. And so they were trying to do this, but they ran into this problem of persistent noise. And they really tried everything and anything to explain it. They found pigeons were basically living inside of their antenna. They found that these pigeons had pooped all over their antenna. And so they even trapped pigeons, prevented them from nesting there. And to commemorate this, there is, in fact, a pigeon trap that they used at the Air and Space Museum in DC. So if you ever find yourself in the Air and Space Museum in DC, I highly recommend going to find this pigeon trap. I think it's a holy grail in this museum. So they couldn't eliminate this persistent noise. And what this means is that it was coming all times of year, didn't depend on the direction. It was literally everywhere. And they called up some people at Princeton who are working on cosmology, and they had predicted that if the Big Bang Theory can explain the evolution of the universe, because everything has been expanding, if you roll back time, everything started from a hot, dense ball of, particles at some point. And so that first light of our universe has expanded and cooled over time to become what we now know as the cosmic microwave background. And they could determine that the temperature of that nuisance signal that they were seeing corresponded almost exactly to the predictions from these Princeton physicists. And unfortunately, the Princeton physicists were essentially scooped. And Penzias and Wilson got a Nobel Prize for observing this cold fossil radiation from the Big Bang. And it's lasted to this day. It's still our best idea of how our universe has evolved. Okay, so we're gonna leave the universe alone and go back to our own galaxy and talk about pulsars. So pulsars are another extremely important astrophysical discovery made possible by radio. They were discovered by a graduate student, Jocelyn Bell Burnell in the UK, and she was hired by her advisor, Anthony Hewish, to discover more quasars. To do this, she spent 2 years laying down these wire cables in a field. A lot of astronomy takes place in fields, it turns out. And so after 2 years of doing this, she was detecting quasars and trying to, measure different signals. But she came across something that she couldn't explain. It was this pulsing source that had an extremely regular period, and it came from the same point in sky, and she saw it night after night. And because it was this pulsing source, this pulsing radio source, she called it a pulsar. The first explanations for this, probably jokingly, were that they were little green men. But in fact, they ended up being the first observational evidence of neutron stars, which is incredibly important, as we know. And so they have been found to thousands and thousands of quantities now, and there are different flavors of pulsars that tell us different things. Some of them, like millisecond pulsars, are extremely stable clocks, rivaling atomic clocks. And since they're spaced throughout our galaxy, they essentially act as a big telescope themselves, telling us about gravitational waves passing through our Milky Way. And so this was Jocelyn Bell Burnell's discovery. This is just an animation of pulsar, so it's constantly emitting this radiation in the radio, but since it's spinning, we only see it every rotation. There have been 2 Nobel Prizes related to pulsars, one for the discovery, and then one many years later for a test of general relativity that was made possible by pulsars. But it's important to note that Jocelyn Bell Burnell, who spent 2 years laying out all of this cable, spent cold nights looking at quasars, was left out of these awards. So I always make sure to pay her homage. Okay, so those were some of the exciting radio discoveries along its history. Now I'm going to talk about things that are going on more recently. The first one are these things called fast radio bursts. So a pulsar astronomer decided to look through some old data that he had and found a signal that was extremely strong and unlike any pulsar that he had seen before. So this is a pulsar kind of plot of frequency versus time. This part doesn't matter, but the signal is extremely strong, much stronger than you normally see. And so he published these results, and we still don't have a really solid explanation for what they are, but then other people started looking for them in the data. And in Australia, they found that there were actually quite a lot of these, and they followed very similar shapes as the initial discovery, but they were way too numerous to have been missed by so many astronomers before. And so this was plaguing the discovery of these fast radio bursts, and an astronomer in Australia nicknamed them paratons, which are these mythical winged elk creatures, and they were really trying to figure out what these were. And some brilliant person decided to plot when most of these paratons were seen as a function of the time of day. And you can see that at about 1 p.m. or so local time, there is this spike in these detections of paratons. What it turned out to be is a microwave oven that was faulty. So the astronomers at the time were actually extremely relieved to have an explanation for this. But what it was is people heating up mugs or their leftovers and prematurely opening the door. And your microwave oven is supposed to stop immediately. This one was faulty, and so it would emit this decreasing intensity radiation. And microwaves operate at radio frequencies, and this was a microwave oven at the telescope, and so they were just detecting this microwave over and over and over. It's one of my favorite stories. But thankfully, we now know how to build microwave ovens correctly, and they are now housed in these thick metal cages at all radio observatories around the world. But we have found so many more fast radio bursts since then. There are telescopes built primarily now to find these things. They are like pulsars, but not like pulsars. They can only be explained to be outside of our galaxy. And so we still don't have quite a perfect understanding of them, but they are already enabling us to study the space in between galaxies, which is really powerful and something that's quite difficult to do otherwise. Okay, so I wanted to finish up by talking about the question that I spend my day worrying about, which is measuring star formation rates in galaxies across cosmic time and putting that all together to try to figure out when our universe was really assembled. And by now you can guess that radio waves are unaffected by dust and are therefore this really wonderful probe of star formation and extragalactic sources. So how does this actually work? Well, we have a spiral galaxy like our Milky Way. Inside the spiral galaxy are regions of star formation, and massive stars burn through their fuel really quickly and are the first things to go supernova very quickly in the context of the lifetime of a galaxy. These supernova create these shocks as that radiation goes into the interstellar medium, and this accelerates electrons to almost the speed of light. Now, galaxies are filled with magnetic fields, and since electrons are charged particles, they end up orbiting around these magnetic fields and emit radio waves as they do so. So we can correspond how much radio emission we see with how much star formation is going on. Now, we can do this, but unfortunately, the radio galaxies that are produced by star formation are much fainter than those that were seen before. So these are the kind of galaxies that were first discovered. These are quasars, or known by their more collective term, active galactic nuclei. I mean, this is extending many, many megaparsecs, which is a big number in astronomy, out into the intergalactic medium. But unfortunately, the radio emission from star-forming galaxies is extremely faint. And we need the most modern telescopes in order to see them back when most of the star formation in the universe was happening. So this is my favorite radio telescope. This is the Meerkat telescope. It's in the Karoo Desert in South Africa, and it's producing some really, really remarkable results about star formation. So I was really lucky to be part of the team that commissioned this radio telescope, and we used it to take the deepest radio image yet taken. I left the noise level here for anyone who cares. It's really low. And what this has enabled us to do is see this really faint radio emission from star-forming galaxies down to the point where the universe was only 3 billion years old. And we can use these radio observations to measure the star formation rates in these galaxies at different times. And we can compare that with the understanding we had from visible and infrared light. And what we see doesn't agree. So this is the idea that we have about how quickly galaxies are forming stars from radio wavelengths. And then this is how quickly we predict or have measured stars forming at visible and infrared wavelengths. And so, yeah, they don't agree. And this turns out to be a pretty big difference. It amounts to something like we might be missing over half of the star formation that's occurred in our universe. And so this is still an ongoing question. This is what I do every day. But ultimately, radio observations are providing this new perspective into some of our oldest questions. They are allowing us to peer through dust and measure how quickly stars are forming. But I do want to be transparent and say radio is not perfect. We don't understand everything about how radio traces star formation. But all I know is that what we are learning is still changing our understanding of the universe. Thanks. So even though radio astronomy has been around for less than 100 years, it's revolutionized our understanding of the universe, and I predict we will continue to find the most unexpected and unbelievably cool things as long as we keep looking. So this is the conclusion of my talk. The history is so interesting. I only scratched the surface, so I included some references on a web page if anyone is interested. You can scan this QR code if you want to read more. But with that, thank you so much, and I'll take questions.
Great job. So we have microphones. Thank you. We'll start with Kathy over here so people at home can hear the question.
Yes, thanks so much. Is that picture right there, does the sky always look like that every night, or does that change from time to time?
Yeah, that's a really good question. So yes and no. Most of this, yes, we do think that stays the same night to night. But there are some indication that this is variable, and that itself tells us something, and unfortunately I can't tell you what it tells us because we don't understand yet.
Interesting. Thanks.
Other questions?
I have one more. I'll ask another. And that is, do you foresee that we'll be able to use radio astronomy to detect extraterrestrial intelligence?
Yeah, so that is something that we've been trying to do for a very long time. So the reason why we look for extraterrestrial intelligence at radio frequencies is somewhat nuanced, and it is rooted in our bias towards looking for life where we know it to be, or something similar to us. And so hydrogen is the most common element in the universe, and it's essential for forming water, which we think is essential for life. And so there's this transition in the hydrogen atom at 21 centimeters, which is in the radio regime. And so astronomers thought, well, if there are other intelligent organizations or beings out there, they might also think the same exact thing and emit at these same radio frequencies corresponding to hydrogen because of its significance. So we've been looking for a very long time and have not found anything conclusive, but we might just have to change how we're looking.
In the future. All right, thanks.
Hi, thank you. That was a wonderful talk. I was wondering, at the beginning you showed charts that dust was highest in the universe, approximately when galaxy formation was highest, and they looked like a very similar plot.
Mm-hmm.
How are those two things related, that we've decreased our star formation and decreased amount of dust?
Yeah, that's a very good question. So it makes sense that the peak of dust corresponds to the peak of star formation, because we know that stars form in these molecular clouds that are full of gas and dust. So more dust indicates that more stars can be forming from them. It's essentially part of their fuel. And so as the star formation goes on, it consumes all this dust into stars. It's no longer affecting our measurements quite as much. It still is, but not as much. And so that's kind of why they follow similar shapes. The dust corresponds somewhat to the fuel of star formation, and so as stars form, it uses up that fuel, and both decline.
There's a little.
Yeah, so Arecibo, I guess, was the biggest single dish radio telescope, and it fell apart. And is it going to be rebuilt, or do we have things better that it wouldn't help us anymore to build something like that?
Yeah, so Arecibo, traveling to Arecibo when I was an undergraduate was what really got me into radio astronomy. So it is a very special place in my heart. And for a time after its collapse, astronomers, especially pulsar astronomers, were debating whether or not to rebuild the facility. Ultimately, it's unclear what its future will be, but there are other similar style telescopes, one of them being the FAST dish in China. So Arecibo is 300 meters in diameter, FAST is 500 meters in diameter. So it has this huge collecting area essential for measuring really, really faint sources.
Well, thank you for an excellent talk. Have you ever correlated your radio astronomy with the Hubble telescopes and the telescopes like that?
Yeah, so if I understand the question, it's have I ever correlated Hubble telescope images with these radio images? Yeah, so that's really essential because radio tells us so much, but we have to put it in context. We have to know that this radio emission is coming from a galaxy or from a quasar. And the only way we can really figure that out is by looking at the multi-wavelength data. And so Hubble is a huge part of that because it allows us to look at optical images of galaxies, yeah.
Yeah, so speaking of Hubble and optical telescopes, so are there any plans or is there any advantage of putting a dish somewhere outside of our planet, like somewhere in space or maybe on the moon?
Yeah, so there are people trying to put a radio telescope in a crater on the far side of the moon, which would be really sensitive because, as we all know, our cell phones and TVs emit a lot of radio emission, and this makes it difficult to detect the faint emission coming from space. And so if you put one on the moon, you have less of those problems. And so there's some actually serious planning going on to see if this is feasible. But I don't think anything conclusive has been decided yet.
How is space dust and radioactive waves connected in our universe?
Can you repeat the question?
How is space dust and radioactive waves connected in the universe?
How are they connected? Yeah, so they might not be connected very much, which is part of the key. So dust, we correspond with like star-forming regions. Like the reason why we see it primarily in the center of our galaxy is because that's where most of the star formation is going on. But we know that dust absorbs starlight and emits at far infrared wavelengths. And so it's not thought that it emits at radio frequencies. Yeah, there are some intricacies, but
What made you choose radioactive waves as your subject of study?
Clearly it's the coolest. Partially because it's detecting a lot of physics going on in the universe. I never really wanted to be an astronomer. I was really into physics. And so I just thought that being able to do the physics of the universe was the coolest job I could ask for. And so doing that at the radio was seemed the most natural to me.
Yeah, I have another question about the image on the screen. It seems very irregular. So how much of the sky are we seeing here?
Yeah, that's a great question. So this image is about 3 degrees across and 2 degrees high. So if you hold out your thumb and look at the sky, that's about half a degree. So you're basically seeing 6 thumbs worth in the sky.
Okay.
So it's a relatively small region, but this is right around where the supermassive black hole is in the center of the galaxy. So this is where most of the activity is going on. They've mapped out the galactic plane farther from the supermassive black hole, and it is still doing some really weird things, but it's not quite as explosive as this.
Okay, thank you.
One last question right here.
Yeah, I'm curious, kind of following up on my previous question, how do we deal with all the noise, all the interference from everything we do on this planet, like, you know, whatever we're getting from satellites, cell phones, and everything?
Yeah, satellites are a really big problem. There is you can buy parts of the radio frequency bands, and so companies do this for their satellite communications and Starlink. But thankfully, some of these regimes are protected by the government for their significance in radio astronomy. But this is becoming more and more of a problem, and it's partially why we have to put telescopes in the middle of the desert in Africa in order to minimize those sorts of sources of interference.
It's the radio version of light pollution.
Yeah.
2 quick announcements. One, we found iPhone. So if anybody's missing an iPhone in a blue case, the Huntington Security has it, so let us know. Second announcement is our next lecture is in 2 weeks, and those tickets are available tomorrow at 10 a.m. And that lecturer is Jeff Rich, who's our education outreach coordinator. You've heard him. Many of you know him, and he'll be talking about his new James Webb stuff, so it should be super interesting. And with that, let's thank Allison for a great talk.